Problem 2.
You're given that in problem 2.
Oh, but I actually found the formulas for x. So part of the problem was actually for you to write down, part of the answer to this problem would actually have been to write x bar equals to blah, y bar equals to blah, z bar equals to blah, which you could do from here. Right? All right, enough. Let me talk your question about the adjoint I should get back to. So the real question, and it also is related to your question, Bethany, which is like, which, is it AB, is it BA? How do we understand all that? What? Oh, purple. Yeah. So let us recall that the inner product from a complex vector space across the complex vector space gives us a complex number, and we had axioms A, B, C, right? What are the axioms? They were that x plus y, z, x, z, y, z, am I right? We had that, did I say you could pull out a constant in the axiom A, or I can't remember? No, that was B? So I had cxy was cxy like that? Was that B? And then C was that xy conjugate is yx. Is true? Okay, and then D was what? Xx greater than 0 for x not equal to 0. Right. Now we proved a proposition that D is equivalent with everything else in play. D could be replaced with that, that the inner product of x and x is non-negative and it's 0 only if x is 0. But this is just a slightly more logically, what's the word? Economal, that's not even a word. Economic, smaller, less greedy. Anyway. Okay, so the question then is components, right? So if we have orthonormal basis, what is that? So even in the complex case, still VI, Vj is Kronecker delta Ij, right? And so if we have x is equal to the sum, I equals 1 to n, of Ci, Vi, the question is, what is Ci? Right? What is Ci? Well, if we look at the inner product of x and Vi, right? So I can put a j here. So this would be the inner product of the sum, j equals 1 to n of Cj, Vj with Vi. Then using axiom A and B, we can pull out the sum, pull out the constants. Then we use the orthonormality, right? This gives me Kronecker delta Ji. Sum dies, we're just left with Ci. So theorem. If x is in a complex inner product space V, then with respect to beta, orthonormal, get x is equal to the sum j equals 1 to n of x comma Vj, Vj. And so it's essentially for the same reason that I want the projection onto a subspace W of X to be the sum, j equals 1 to k of X with, let's say, Wj, provided the span of, W1, Wk equals to W, and this is orthonormal. See, because the boxed formula that I just wrote down, it should become the projection formula in the case that W is the whole vector space, right? So like these things have to work together in that sense. And then the other thing is, when you're doing the Gram-Schmidt, if you really think about what you're doing, let's see, let's kind of sort through it for a second. So suppose we're doing Gram-Schmidt on U1, U2, UK. All right, suppose you've reached the jth one. So suppose J is somewhere in here. Right? So essentially, you already have, let's say, beta J, which would be U1 prime prime, Uj prime prime, right? This is orthonormal basis for the span beta J. You could think of it that way, right? I mean, so you could think about the span of all of them forms W, right? But you're building up like a bit of W as you go on. So if I think about Uj, good grief, Uj plus 1, yeah? I want to take it. I want to make Uj plus 1 prime. I want to make that an element of the, I need to give this stupid thing a name. Let me call this span of this Wj, if you don't mind. So I want this to be an element of the perp to Wj, right? I want to get rid of the piece of the j plus 1th vector, which is in the span of everything that's already there. That's the Gram-Schmidt process. And so how do you do that? You say Uj plus 1 is equal to the orthogonal projection onto the Wj space of Uj plus 1. Uj plus 1 prime is that. But what is this? This is Uj plus 1 minus the projection onto the Wj space of Uj plus 1, right? But what is this? This is the sum. Let's say I equals 1 to j in this case of, well, Uj plus 1 with U sub I prime prime, U sub I prime prime. So I finally found an answer to your question, Bethany. We should make it like, so the prime primes should go in the second slot because we're taking components of the next vector in the list. So this is the one that should be first, the thing that we're orthogonalizing, if you will.
So then in the more general one, like the x and the wj, if you do that for all of the j's, then that's the coordinate vector?
That's also true, yeah. So the coordinate vector of x with respect to beta is x with v1, x with v2, x with vn. Very true, yeah. Now, how do you calculate the adjoint of a map? I can think of 3 strategies, Emma. So like 3. By the way, so in the case that we have reals, we shouldn't really think of it this way. And when it's the real, when we're looking with a real vector space, we should really, it's probably best to think of it as being a bilinear. It's a bilinear map. In other words, you have linearity in both slots. It's got a symmetry. It's symmetric. You can the inner product of xy is the inner product yx because there's really no complex conjugate in a non-trivial sense in the real vector space. And the last part D is essentially the same. So in other words, it behaves like a dot product in the case of a real vector space. So when I write out the solution today, I will write that out for you guys. So let's see here. The definition of the adjoint of x, I said, was what? Oh, I'm sorry, we're out of time. But so if you look at it, it has to be. So here's what I'm annoyed that I told you guys wrong. At least some of you. So I believe the x goes here is the thing. So if you switch the x, it is just generically true that T of x is the sum of vi, T of x, vi. This is the basis expansion of T of x. And I'm afraid I told you that formula for T star. I claimed that this was T star to some of you, maybe like Monday or Tuesday this week, unfortunately. I'm sorry about that. Because the adjoint has to have the T of vi over here like that. That said, the easiest way to calculate the adjoint is this. If it's a real vector space, if I got something like this, what I do is I write down the matrix. And then the cool thing is the matrix of the adjoint, in the real case, is the transpose. Sorry, this is all T's. Let's see here, 1, 3, minus 1, 0. That's the matrix of the adjoint, so what's the formula for the adjoint? There you go. There's the adjoint of a 2 by 2 real. So one of your homework problems was like that. The fastest way to do it is to use that the matrix of the adjoint is the conjugate transpose of the matrix of the transformation. But I'm also fond of just working it directly from the definition like that. I'll try to do both in the solution that I finally write today. So make sure you know the basics. Like a lot of this test is just going to be pretty basic stuff. I mean, it's not. I don't need to be tricky on this test, I would say. Yeah. Like calculate an eigenvector for an actual